Okay, good evening, good morning, good afternoon from wherever you're joining. Quite a number of people signed up, so I do hope we have quite a significant number of show ups. Uh, Still have a few minutes to go. Okay, guys, good morning, evening, afternoon. Welcome. We still have a few minutes before we kick off this talk on challenges in machine learning. We'll start in 2 minutes from now. Okay, guys, can you hear me loud and clear? Seppa, can you just let me know whether all is okay to go? All is okay to go. Okay, um, 1 more minute because it's only 6 o'clock now. So, okay, guys, guess we can start. As I said, good morning, good evening, good afternoon. From wherever you're joining us. In my case, it's good evening. My name is Bart Bassens. I'm a professor of big data and analytics at the Catholic University of Leuven. In Leuven, is a city where I'm based right now. It's a city pretty close to Brussels, for those of you who haven't heard of it before. It's about 20 miles away from Brussels. It features one of the oldest and obviously one of the best universities worldwide, more specifically the Catholic University of Leuven, which was founded in 1425, so quite a long time ago. It's not the oldest. The oldest one is situated in Italy, in Bologna, but we come quite close to it. So I'm working at this university as a professor of big data, analytics, data science, whatever you want to call it. I also have a part-time appointment as a lecturer at the University of Southampton in the United Kingdom. My research is big data and analytics, and we, together with my team of PhD and postdoc researchers, we study the development of new algorithms as well as innovative applications thereof. Innovative applications across a variety of different application fields, ranging from credit risk modeling, which was the first application area I worked in, to fraud analytics. We did a lot of work in fraud analytics as well, and also in customer lifetime value modeling. Throughout this talk is entitled Challenges in Machine Learning. I'm going to try to embed as much as possible some of our recent research findings across these various fields. I also have a YouTube, Facebook, and Twitter account. In case you would like to be connected on any of those, feel free to connect on YouTube, Twitter, Facebook, or Twitter. It's called Each Time Data Mining Apps. I also, together with a colleague professor from the Catholic University of Leuven, who's now working at the University of Antwerp, started my own online course business. It's called bluecourses.com. It's an online course business which features all kinds of online courses, which consist of a set of pre-recorded videos together with Python, R, SAS code, quizzes, etc. And upon successfully completing the course, you will also be awarded a certificate. And we have courses on a variety of different topics on credit risk modeling, machine learning essentials, fraud analytics, recommended systems, customer lifetime value modeling, and text analytics, etc. And we also contribute our share to sustainability because we pledge to invest 20% of our EBIT, of our earnings before interest and taxes, to companies cleaning up our precious oceans from plastic. I also written a few books on big data and analytics. Some of them are application oriented, some of them are more at the methodological level. Here you can see some of them listed on credit risk analytics, fraud analytics, profit-driven business analytics, database management, etc. My most recent book is a book that I wrote together with my colleague, Professor Seppe van der Broeke. It's this book. It's Managing Model Risk. And part of what is written down in this book, only a small part of it, I will also touch upon throughout this presentation. Model risk is the risk of models, analytical models, data science models not being perfect. And since these analytical models more and more steer strategic decisions of firms, it becomes very important to be aware of model imperfections and how to deal with it. And that's something that we extensively cover in the book and that I will briefly touch upon throughout this talk. Okay, so here we go. So what I'm going to do is I'm going to kick off with a refresher of the machine learning process model, just briefly highlight the various steps that it entails, and then we're going to zoom into machine learning model requirements. So if you're building a machine learning model, what are the requirements that it should satisfy in order to be successfully deployed into production? Then we're going to say a few words about feature engineering and model risk, and finish this webinar with some closing thoughts. Here you can see the machine learning process model highlighted, and there's various industry standards available for it, like IBM has its CRISP-DM process model, SAS has its SEMA model, but they all boil down more or less to the same type of procedure, which you see highlighted here. So we start from identifying a business problem. That business problem, it's very important that it's clearly defined. That could be identifying fraud, that could be identifying churn. Churn means that a customer, for some reason, starts to get dissatisfied with the product or service you're offering, and that he or she will leave your firm and go and buy it elsewhere. So the first thing that you should do before you start doing machine learning is clearly, unambiguously, very accurately define your business problem. Like we want to define churn, we want to define people that cancel their contract with our firm, or we want to identify fraud. And if you say fraud, you have to very carefully define what is fraud, what type of fraud. Are you looking at credit card fraud? What type of credit card fraud? Are you looking at insurance fraud? Are you looking at identity theft? Are you looking at anti-money laundering, etc.? So it's really important that you very carefully define your business problem at the outset of your machine learning process model. And once you've carefully done that, and that's a very close collaboration between the data scientist and the business user, you're going to start identifying all types of data sources that could come in handy to solve your business problem using machine learning or analytics. And the golden rule there is the more data, the better. And you start assembling data, you start assembling socio-demographic data of your customers, maybe some payment data, maybe some transactional data, maybe some unstructured data as well. Think about textual data or imagery. And the more data, the better, because in the next step, what you're going to do is you're going to bring it together into a staging area. That could be a data lake, that could be a data mart, or for even very small scale projects, could even be an Excel file as well, right? So there's nothing wrong with using Excel if you're doing small scale machine learning or small scale analytics. But if you're doing bigger scale machine learning or analytics, obviously you need a bigger data staging area, such as a data mart, a data warehouse, or a data lake. And what you will then see is that much of these data will contain noise, will contain irregularities that need to be cleaned up using a subsequent step. So in subsequent step, cleaning up the data, you're going to take care of things like outliers. Imagine that somebody's age is minus 20 years old. That's an outlier. You have to take care of that. Somebody's income is exceptionally high. It's also an outlier. Somebody's income is missing. Somebody's age is missing. So all of this you will take care of during this cleaning step. Next follows the transformation step. And in the transformation step, what you're going to do is you're going to prepare your data in the best optimal way to do machine learning or analytics in the next step. And it's very important that you do this transformation step very carefully. Like one of the topics that we will come back to later on is feature engineering. A very simple example of feature engineering is that based upon the date of birth, you're going to derive the age of your customer. So deriving the age of the customer is a type of feature engineering that you will do during this transformation step. In marketing analytics and in fraud analytics, data scientists will often use RFM variables that you may have heard of. R stands for recency. How long ago since a customer made a transaction? How long ago since a customer made a purchase? Frequency, F stands for frequency. How frequently is the customer making transactions or making purchases? M stands for, you may have guessed it, monetary. So what's the average monetary amount for which the customer makes transactions or purchases at your firm? And these RFM features are typically used in marketing analytics and fraud analytics, and these are then constructed using these during this transformation step. Next step is the analytics or the machine learning step. And note that the terms like machine learning, analytics, data science, or data mining, they're all referring to the same thing. They're all referring to extracting mathematical patterns from a specific data set. Mathematical patterns or mathematical formulas that represent customer behavior in a very specific way. And here, as you can see highlighted in my slide, basically what you want to do is you want to come up with a machine learning or analytical model that discriminates between the two red dots, let's say that those are the fraudsters, and all the green dots, let's say that those are the non-fraudsters. And there exists a plethora of machine learning techniques to do that. There's like regression methods, decision tree methods, there's ensemble methods, there's neural networks, there are deep learning methods, and so on. And obviously, when you build a machine learning model, it needs to be properly interpreted, it needs to be evaluated before it can be successfully deployed into your production environment. These are all activities, the interpretation of the machine learning model, the evaluation thereof, and the deployment that make up the post-processing step of the machine learning process model. So you can see that this is an entire process model, and very important, it's not a strictly linear process model in the sense that sometimes during the transformation step or during the machine learning step, it may well be that you have to go back a few steps in order to clean something in a different way, or to gather more data, or to gather very specific sources of data, etc. So this is how the machine learning process model looks like. And a first important question is, if you build a good machine learning model, what are key model requirements that it should satisfy in order to be successfully brought into production afterwards? And currently, both me and SEPA, because this is an initiative that me and SEPA, this thing, the data chat, is an initiative that me and SEPA have developed. And we collaborate with quite a lot of firms worldwide. And what we do quite a bit of consulting in the sense that we help firms worldwide build their analytical models, not only building them, but also validating them. That's actually what we're doing quite a lot, because we want to see whether machine learning models satisfy all the requirements that they should satisfy. And there's various of them. First of all, there's statistical performance. Obviously, a machine learning model, which is built from data, should capture the patterns that reside in the data in a statistical, meaningful way. And there exist various types of statistical performance metrics, and some of them are more important, some of them are less important, and it highly depends upon the type of data and the business problem that you're trying to solve. So it highly depends what business problem you're trying to solve. That will largely impact what type of statistical performance metric you should be using. But besides statistical performance, there are also other requirements that a machine learning model should satisfy. There's the requirement of interpretability. More and more, machine learning models should be interpretable. That means that you can no longer use very complex mathematical formulas, which are often the result, for example, of a deep learning exercise, to steer your strategic decisions. Imagine that you're a bank and you're developing credit risk models, and you're using very complex mathematical formulas as they come out of a neural network or as they come out of an ensemble method. Well, given the impact of credit risk models nowadays, no national banking regulator will allow you to use those complex models, because they will enforce you to come up with models that are easily interpretable, such that if you decline credit to a particular customer, you can easily give him or her a justification of why you are not giving him or her credit. Next is operational efficiency. Right? You see that analytical models are more and more being run in real-time online environments. So that means that operational efficiency becomes very important. Think about credit cards, for example. So if I stole somebody's credit card and I make a fraudulent transaction with it, obviously the credit card processor wants to block it as soon as possible. As soon as I initiated the transaction, it wants to block it as soon as possible after that. There's also profitability, because at the end of the day, if you're a company, what do you want to achieve with machine learning? You want to boost your profits or cut your costs, which are two sides of the same coin. And that's very important, is that we also evaluate our machine learning models in terms of profitability. And last but not least, there's the privacy and ethics aspect. More and more, we can do more and more with machine learning. There's more and more data available. Think about social media data that is available. Think about public data, Google data, Google Street View, Google satellite image, etc., Google Trends data. All of this data becomes available, and all of a sudden opens up a huge window of opportunities for machine learning to tap into. And it becomes, the possibilities become humongous, which means that from a privacy and ethical perspective, the challenges also become quite substantial. I will zoom into each of those 5 criteria into somewhat more detail in what follows. Obviously, I cannot get, this is only um, a very short talk, so I cannot get into a lot of detail into each of these. But if you want more information, feel free to let us know. Statistical performance, there exists quite a lot of different types of performance metrics, like depending upon whether you're doing predictive or descriptive analytics. If you're doing predictive analytics, in fact, what you're trying to do is you're trying to predict something, right? And the thing that you're trying to predict could be something that is continuous, like the customer lifetime value. That's a continuous number between 0 and 10,000, let's say, or between 0 and 1 million, depending upon the context. Or you can also predict something categorical. If you're predicting whether a customer is a fraudster, yes or no, a churner, yes or no, then you're predicting something categorical. And whether you're predicting something continuous or something categorical will have an impact on how you're going to measure the statistical performance, right? Because if you're predicting something continuous, then you will make use typically of R squared, of Pearson correlation, etc. These are statistical performance metrics for continuous targets. If you're predicting something that is categorical, like if somebody is a fraudster, yes or no, or a churner, yes or no, then you're gonna more look at things like sensitivity, specificity, type 1, type 2 error, and also, very important, a metric which is currently being used by quite a lot of firms worldwide. It's called the ROC curve, Receiver Operating Characteristic Curve, which kind of depicts the sensitivity versus 1 minus the specificity for various types of cutoffs. And that's a measure that is nowadays being used by every bank uses it in its analytical reporting, for example. But statistical performance is only, as I said, is only one important machine learning model requirement. Another one is model interpretation. And I have to say that this, however, highly depends upon the application and the business analyst, because certain types of applications necessitate the usage of white box models. When we say white box models, we mean machine learning models or analytical models that are very easy to understand. And there's two that I can think of right away. Those are regression models, linear regression, logistic regression. Logistic regression is basically linear regression, but tailored to a classification setting. It means that you're assuming that your target variable is not continuous, but rather categorical instead. But it is a very simple model. I mean, if I would explain, if you would give me 10 minutes, then I can explain a logistic regression and you will fully understand it. Just like decision trees, they're very simple models. They're very readable. They're very interpretable. They're very transparent. That's why we call them white box models. But it comes at a cost. Their simplicity comes at the cost of them not being very powerful in terms of modeling complex patterns in the data. So if you really want to model very complex patterns in the data, you have to resort to more complex, sophisticated, advanced modeling techniques, which essentially give you very complex mathematical formulas. And the techniques that I'm thinking of are like XGBoost, which is an ensemble method. That means that instead of one decision tree, you're now going to build hundreds of decision trees that collaborate together in a smart way so as to give you an ensemble that gives a better performance than a single decision tree, right? Random forests are also an ensemble of decision trees whereby the ensemble is constructed in a somewhat different way. And then obviously we have neural networks and their deep learning variants, which are very complex machine learning models. That's why we call them black box models. And in certain types of settings like credit risk modeling, in credit risk modeling, you will see that the machine learning models are so important that they're regulated by national regulators. Like in the US, I don't know whether people from the US are joining us, but in the US, it's the OCC or the Federal Reserve that is actually inspecting the credit risk models by banks like Bank of America, HSBC, to see whether they have been appropriately constructed and whether they are sufficiently white box. In the UK, it's the Bank of England. Here in Belgium, we have the National Bank of Belgium, which is doing this job, and so on. These white box models are also needed in for medical diagnosis applications. Think about the COVID disease and so on. If you want to study how what triggers COVID, then obviously you want to use a white box model because you want to see what are the influencers there. Fraud detection is also an area where we need white box models. Why? Because it's not only about detecting the fraud, but it's also about preventing the fraud. And how can you prevent the fraud? You can prevent the fraud only if you understand what types of fraud you're being exposed to. So you really have to have a white box machine learning model there in order to come up with smart fraud prevention mechanisms. We don't need white box models in every type of setting, like in response modeling. Response modeling is the type of application where you're going to model whether somebody's going to respond to your marketing campaign, yes or not. And your marketing campaign could be a banner that you put on the web, could be an email that you send out, could be a brochure or a flyer, a physical one then that you send out to certain types of customers. And in response modeling, you're then going to see which customers are likely to respond to the message, to the marketing message you're sending out. Well, in these types of applications, you will often see that companies are still using those black box models because there's no need for explanation. You just want to send out your marketing message to the customers who are most likely to respond to it, right? And you don't need to understand why, as long as they respond. That's what you care about. So it does depend upon the setting where you're going to use, whether you're going to use white box models or black box models. And there exists, again, a plethora of techniques to make complex models white box, right? And Seppa and I do quite a lot of research, oftentimes in collaboration with firms, to make complex machine learning models interpretable using all kinds of features that have been made available in the literature, some of which we have also contributed ourselves. What is, for example, partial dependence plots, individual conditional expectation plots, Shapley values. Shapley values, for those of you who are a little bit more versed in machine learning, Shapley values are being used a lot nowadays by firms. I'm collaborating with one French bank, one French big French bank in credit risk modeling, where we're using complex models, but we add Shapley values to it in order to make it to make the credit decisions more interpretable to the business users, Lime, etc. In our research, what we've did, for example, we kind of like to work with rule-based systems. A rule is a simple if-then formulation of a certain set of conditions that need to be satisfied in order for an action to trigger. And it builds further upon what I did in my PhD, for example. And what I did there was we started from very complex models like neural networks. Neural networks are complex models because they kind of consist out of neurons that are connected with weights that you learn from the data using a sophisticated machine learning algorithm. And you structure those neurons into layers, right? So you have this input layer right here that has inputs, right? This is a credit risk modeling example where you have whether the loan term is bigger than 12 months, how much is on the savings account, whether the person owns property, yes or no. All of this is being fed into the neural network. There's some processing, some transformations that take place, which is then being fed to a subsequent layer of neurons. And you can have as many layers as you want. The more layers you have, the more complex, but also the more powerful the neural network becomes. And then a final layer will decide whether the applicant is a good or a bad payer. And obviously, when you look at this neural network like that, and with all the complex transformations that take place, it's a complex, opaque, intransparent, unreadable model. I cannot go to the credit risk manager and say, look, I found a very good neural network that has an excellent ROC curve value. Still remember the metric I mentioned earlier, and that will help you make your credit scoring decisions. He or she will say, no, I'm not going to use it because I don't understand what weights come from, what they represent. I don't understand the transformations. So he or she will be reluctant to use it. So what we did in our research is we started from a network like that and we extracted business rules from it because business rules are a lot more interpretable. They're simple if-then rules. So you can see a simple if-then rule that we extracted from the network. And by providing a set of rules that give you the same performance of the network, then basically you end up having a very interpretable machine learning model. This is actually the set of business rules. So you can see that there's like 6 business rules that give me the same performance as this neural network. And obviously, which one would you favor if you were to make a credit decision? I think you would favor this, right? Because it gives you a white box, nice reason of why you are declining credit to a certain customer. You can see if the term is bigger than 12 months and the purpose is cash provisioning and there's a low amount on the savings account, and the number of years client is lesser than or equal to 3, then the applicant will be labeled as bad. And we have various types of rules like that that we can then list and that we can then very easily understand, but also very easily deploy, because there's nothing more easy than if you work in a production environment like Java or any type of other programming language, than just programming a set of rules that help you make a decision. Okay. And in fact, in our research, we focus a lot on this interpretability aspect. We took it one step further, represented it as a decision table, which is a tabular representation of a set of decision rules, of a set of business rules, which takes the interpretability, as I said, to a next level. Right? So here you can see this is a decision table which just looks at is there some money on the savings account, yes or no. If it's below a certain threshold, we need to look at the economic sector the person is working in. If it's sector C, that was a kind of sector that obviously we cannot say what sector this is because this is based on real life data, then the applicant was considered as bad. Otherwise, we have to look at the purpose, whether it's cash provisioning, second-hand car, other. So you kind of navigate this decision table in a top-down way, so until you arrive at a decision whether the applicant is good or bad. So that's the whole idea of adding interpretability to a neural network. Start from the neural network, extract if-then rules from it, and then represent it as a decision table. Operational efficiency is also something that is very important in certain settings, not in all settings. Let's give you an example of a setting. We did quite a lot of work on fraud detection, and in fraud detection, we typically use quite a lot social networks. And when we say social networks, I'm not referring to Facebook or Twitter, but we're referring to networks of entities. Like we did a case study in credit card fraud detection where we build a network, and the node there we had two types of nodes in a network. So we had credit cards, this is one type of node, and we had merchants that process credit card transactions. Because oftentimes you will see that fraudulent transactions take place at the same merchant, right? And typically this merchant will process quite a lot of fraudulent transactions, and then also every now and then a few legitimate transactions to cover up his or her activities. So what we did, we got a data set from a real life telco, a real life credit card provider. We built a huge social network. We did the inferencing, we did the machine learning. We built a very powerful machine learning model to detect fraud. And at the end of the day, we had an exceptionally high statistical performance. So we were capable of detecting fraud in more than 90% of the cases, right? Which was quite a lot. We were very happy with that. And then we started to talk to the IT guys because we wanted to bring our model into production. And the IT guy said, look, there's the 8-second rule. And the 8-second rule stated that as soon as a transaction is initiated, you have 8 seconds to block it, right? So can your machine learning model make that decision within 8 seconds? Obviously, we bounced the ball back immediately and we said, look, can your IT infrastructure allow us to build that social network, do the machine learning, do the inferencing, and then label the transaction as possibly fraudulent, yes or no? And we already knew the answer. They said no, our IT infrastructure is not mature enough, is not sophisticated enough, is not powerful enough to do that. So what we had to do there is basically we had to take it one step away from the social network. We knew we were capable of detecting fraud very accurately, but the IT infrastructure was lagging behind. So we had to sacrifice part of our model performance in order to get some operational efficiency, to be able to comply with the 8-second rule and to say, look, we are now, by using other types of features, by using other types of machine learning techniques, we are now capable of making a decision within 8 seconds, but it is less accurate than if we would have been able to use the social network instead. So you see that operational efficiency in certain types of settings is really a key concern when you're building your machine learning model. And it's something that you should be aware of at the outset of the machine learning process model, because that allows you to think a little bit more carefully about the types of data you're going to use, about the ways you're going to transform it, and about the machine learning techniques you're going to unleash on it. Operational efficiency is not always a concern. It's not a concern in credit risk modeling. So if I go and apply it to my bank for credit risk, what they do, in fact, I did this recently using, I was put through a scorecard that I validated myself, so I got accepted, which is good news, by a bank. So what you do is you provide all kinds of information. It takes them a few days. So there's the operational efficiency. It's not that they need an immediate decision, right? But in certain types of settings, operational efficiency is a key concern. And then we have profitability, which is the bottom line impact, because at the end of the day, what do you want your machine learning model to do? As I said, you want it to boost your profits or cut your costs. And profitability, if you look at many firms that start making their toes wet in the area of using profitability in machine learning, the first thing that they're going to do is they're going to use it for model selection. That means they have some techniques like regression, they have decision trees, some ensemble methods, maybe some neural networks or deep learning methods. And what they're going to do is they're gonna evaluate them based on profitability. They're going to look at what's the cost of a false negative, what's the cost of a false positive, and then they're going to use a validation or a test set to look at what model gives you the best profitability. So the winning model is then selected based upon that profitability measure. But what we did in my research group, me and SEPA, is we took it one step further because we said, look, model selection based on profitability is a good thing, but if you want to be a little bit more sophisticated, you're going to embed profitability directly in the model construction process. And that's why in certain types of areas, and we do a lot of work in fraud, in churn, and in credit risk modeling, we came up with profit formulas. And I'm not going to explain this. It's too late in the evening for me to explain this integral. But this basically what we did is we built profit models, profit formulas for churn prediction, for credit risk modeling. We have one, and recently we had one for payment transactions fraud as well. And that the latter was developed. I can say that because they sponsored the research, was developed in close collaboration with the well-known bank BNP Paribas Fortis. And what we did was once we had this profit formula well defined, well framed, we directly embedded into the machine learning model construction process. And we developed extensions of well-known machine learning techniques. Like instead of logistic regression, we developed ProfLogit, because a traditional logistic regression, what it does is it chooses the weights, the parameters, or builds the model in such a way that it optimizes a statistical objective function. For logistic regression, this is what we call a maximum likelihood or a cross entropy error function. But what we said is we said, look, we're not interested in that likelihood thing, because there's no person from the business that cares about likelihood values or likelihood ratio statistics or p-values. No, we're going to stick to the model formulation of logistic regression, but we're going to have it optimize profit directly instead. And that brought us to ProfLogit. And then we did the same trick with decision trees, right? Decision trees try to minimize the impurity or the chaos in your data using all kinds of metrics like the entropy, the Gini, chi-squared metrics, and gain, etc. What we said, this is not what matters to business people. Nobody cares about entropy in data. Everybody cares about having a decision tree that gives you profit. So using those profit measures, which we developed for churn, which we developed for credit risk modeling and fraud, we built ProfTree, which directly optimizes the profit for a particular type of data sets. And you can then very nicely see the difference. Here you can see this is on a real life data set, for example, and that's a traditional decision tree, right? It's a CART decision tree. It stands for classification and regression trees. And that gave us a profit per customer. Here you can see this. Well, let's first go through the tree. So here, if active months is bigger than or equal than 9.5, then you go to this leaf node. If it's less than 9.5, then you go to this node. Then you have to look at active months less than 7.5, then you arrive in a leaf node. Otherwise, you have to look at the contract period. And that's the decision tree that was built using a traditional decision tree algorithm, which was named CART. And that gave us a profit per customer of about 12.58 euros. And then we unleashed our Prof3 onto the same data. And remember, Prof3 directly optimizes the profit. Doesn't look at CART, looks at the Gini measure, right? The Gini impurity measure to measure the chaos in your data. But Prof3 directly optimizes profit. And what you do see is that you see that there other types of splits that pop up that look at the revenue, that look at the region, the overdue amount. So they're more biased, deliberately biased towards the profit goal that you're aiming for. And the profit is higher. Now we have a profit of 13.77. So the difference is about 1.19 euros per customer. Obviously, when you have thousands over hundred thousands of customers, that can turn out to be a huge, substantial number. Privacy and ethics is also very important because, as I told you, more and more data becomes available about our customers. Think about, in Belgium, we have the Corona tracing apps, for example, and all the data that is being now stored and to identify how Corona spreads, etc. All of this also comes with privacy and ethical challenges. And we do face a lot of them ourselves as well in our collaborations with firms. First of all, there's the GDPR, Global Data Protection Regulation, which is important in Europe. But I mean, it can get very complicated. Like, can we use gender or age in insurance or credit scoring? In most Western European countries, you cannot, despite the fact that gender and age are the most crucial elements in any type of machine learning model. Men are more risky than women when it comes to credit risk, when it comes to churn, when it comes to fraud, etc. But yet we cannot discriminate on that, which is a good thing for us men, right? Um, Age is also very important. Oftentimes you will see that older customers are less likely to be fraudsters or less likely to be defaulters and so on. But again, we cannot use it. But it becomes very interesting because um, you cannot use age to discriminate in most settings, but what some firms do is they use a predictor in their machine learning models, which is called time on books or years client. For how many years has Bart been with us, right? So I've been with my bank and my telco operator for quite a long time. I'm not the type of guy, hopefully none of my suppliers is actually uh, now listening to this talk, but I'm not the kind of guy that churns a lot. Um, so um, Actually, what you see then is that you start having a correlation between time on books or number of years client and age. So despite the fact that age is not part of your machine learning model, you can have other elements that are part of it that are highly correlated with age or even gender if you want. Another thing is, can we use Facebook, Twitter data, right? So every insurance firm and lots of banks, I get those questions quite a lot because banks want to use Facebook data, Twitter data for fraud detection, for example. This is very important, but also for credit scoring because in credit scoring, you oftentimes see the principle of homophily. And homophily means that people are connected to other people that are quite similar to them in economical sense. That the economic the economic in terms of economic wealth, you will often see that strong correlations between you and your Facebook friends, right? And that's very valuable information to leverage for credit scoring. Can we use Google Street View for credit scoring or for insurance or for fraud detection? These are all questions that pop up as you start thinking about analytics and as you start thinking about leveraging innovative sources of data, and which are not always that easy to answer. I can oftentimes answer what is possible from an analytical or machine learning perspective, but sometimes I cannot answer from a privacy or ethical perspective because it gets too challenging for me as well. Like, can we use your phone detail records for credit risk modeling? What we found was we collaborated with one telco provider in Argentina that was also providing credit to its customers. And they approached us and they said, look, we want to see whether, based upon the phone detail records, based upon who you call, can we also predict your credit worthiness? And obviously, everything was, I mean, the customers were appropriately informed about their phone detail records being used for credit scoring purposes. So we got a very clean, neat data set, which was privacy compliant with all regulations that were applicable in Argentina. And then we could very easily find out whether who you call tells us something about whether you're credit worthy, yes or not. And surprisingly, we found that you can very well predict credit worthiness based upon who you call because of the principle of homophily, because you tend to call people who are in the same economic circle, who are in the same, who have more or less the same economic wealth as you are, which is very valuable for credit scoring. This opens up this at first sight you think this is dangerous, right? So I mean, if your bank would ask you access to your phone detail records, you would say no, stay away from them. But in developing countries, or for poor people, or for people who access the credit market for the first time, or for minorities, ethnic minorities, for example, um, that could open up windows for financial inclusion. Because in developing countries, most African countries, for example, banks don't have any historical data about their customers, right? So they don't have it in a nice, either they don't have it or either it's not readily available. But phone detail records are very easily available or very readily available. And by providing that, or by asking customers whether they can get access to that to their phone detail records, it could give them also a means to get access to the credit market, to get credit. So privacy and ethics is something that is, when you start thinking about it, what I've learned is something that could be seen as a danger at first sight. When you think a little bit further about it, could also present an opportunity for specific types of customer populations. We have a very exciting paper on that in case you would be interested. I also would like to say a few words about feature engineering, because that's also a topic that we're working on, and we did. Sepp and I do quite a lot of consulting for firms. As I said, we built we don't build the models ourselves, but we help firms worldwide building models. So, for example, I collaborated with companies like HSBC, like Bank of America, some banks in Asia, but also the government. I collaborated with the U.S. government, with the U.S. Marines, with the U.S. Marine Corps, with MI6, and so we assist a lot of firms in building models, but also validating them. That's also something that we do quite a lot these days, that we inspect how models were built by firms, and then we help them validating them, because model audit is also a very important activity. But I'm going to come back to that later. And one question we always get is when firms start building their models, they ask us what techniques should we use, and we have our favorite techniques. We know what techniques work well in what settings, so we can give very precise advice on that. But one thing that we always come back to as well is feature engineering. Feature engineering means that you carefully pre-process your data, transform your data, so as to give the machine learning technique the best possibilities available to arrive at a good model. And there exist many types of feature engineering techniques. And just to give you an idea of what it is, here you can see a very simple example, which I borrowed from this website right here. Um, X and Y represent geographical coordinates. And in the middle of the X and Y coordinate, there's a supermarket located. So there's a supermarket located right here, right, where my mouse pointer is, the middle of the plot. And there's obviously customers living around that supermarket, and there's the blue and there's the orange customers. And then the customers are being categorized into two colors. The blue colors are the profitable customers, and the orange customers are the non-profitable customers. And obviously, as you can see from the plot, it's quite straightforward to see that profitable customers live in close proximity to the supermarket, whereas orange customers, which are not profitable, live further away. And what you can now do is you can now try and use a machine learning model that discriminates the blue customers from the orange customers. And believe it or not, there's a circular pattern in the data, as you can see there, and that's very tricky. That's challenging for machine learning models. We can do it with machine learning models, but it gets you will very quickly arrive at a very complex machine learning model. Like a decision tree cannot cope with that. A linear or logistic regression model cannot cope with that. A deep learning neural network can do the job, but then you have a very complex model. So what's a smarter way is, instead of working on a complex model, is working on the X and Y axis and represent something different on the X and Y axis. What you can do is you can take this and represent it in polar coordinates. Some polar coordinates are something that you may remember from your lessons of mathematics in high school, where you have where you represent data not using traditional Euclidean X and Y coordinates, but using vectors, whereby you look at the angle of the vector versus a reference axis, and the size of the vector. So the theta is the angle of the vector versus the reference axis, and r represents the size. What you see is if you take this data set and you represent it in polar coordinates, so you engineer, that's what we do when we do feature engineering. So we engineer the original data into polar coordinates. All of a sudden, it becomes linearly separable. Everybody to the left here of this line around 2 it is, to the left of 2 is blue or profitable, and to the right of 2 is orange or non-profitable. Thinking about representing your data not in a Euclidean space, but in a polar coordinate space system is an example of feature engineering. And it goes much further than that, but unfortunately, I don't have the time to elaborate further, but there exist various types of techniques to do very clever feature engineering, like transformations, like feature combinations, etc. Seppa and I recently did a special issue of the Machine Learning Journal, which is a well-established journal in the field, on this very topic of feature engineering. Okay, that brings us to the topic of this very exciting book on model risk, which I can highly recommend, especially since I wrote it myself together with Seppa. And the reason Seppa and I have been working in machine learning for, I think, more than 2 decades right now. We witnessed quite a lot of machine learning models in industry. We're not the type of ivory tower researchers that focus on a new technique, which is nice from a mathematical standpoint, but which doesn't have any business added value. Seppa and I like to collaborate a lot with firms. Like Seppa is now collaborating with Brussels Airport firm, with KBC. I'm collaborating with I'm collaborating myself with Allianz, with BNP Paribas Fortis, with Ageas as well, insurance provider, with Coca-Cola. I've collaborated with quite a lot of firms, and we wanted to write down much of the experiences that we learned, mistakes that were made, risks that were introduced into the development or the deployment of machine learning model. And the reason we wrote this book was further accelerated by some findings by FICO. FICO is a well-known customer scoring organization that was founded by Bill Fair and Earl Isaac in the 1960s of the previous century, and they were found. I once taught a course for FICO a long time ago. They're based in San Rafael in San Francisco. So FICO came up with a report in 2021, so this year, that stated that 65% of the companies cannot explain how a specific machine learning or artificial intelligence decision is made. 73% have struggled to get executive support for prioritizing machine learning or artificial intelligence. We can use both terms interchangeably, ethics. Only 20% of the firms actively monitor their machine learning models in production, which is quite worrying if you ask me. And 30% of the organizations report an increase in adversarial and other attacks against their model. So these are all examples of model risk, and that's why we decided to write this book on it. And if you write a book on model risk, then the first thing you have to do, being an academic, is define model risk. And Seppa and I define it as the risk of expected or unexpected loss. And when we say loss, we are predominantly focusing on economic loss resulting from the inadequate development or usage of analytical or machine learning models across all business units and activities of a firm. Right? And this entails various types of risk, right? So if I look at the table of content of the book I have right here, which is available on Amazon, by the way, I need to do some commercial, right? We talk about data risk, we talk about specification risk, development risk, validation risk. These are all different chapters. Operational risk, security risk, and managerial risk. And I'm just going to highlight some of them, right? So data risk is the first one of them. And um, everybody has their hobby. So, and I have a hobby as well. And one of my hobbies is I'm very fascinated by history. So I like to, I'm currently looking at a Netflix documentary on, uh, on Japan, on how the state of or the country of Japan got established in the Middle Ages. It's very exciting. But I also read a lot of books on World War One and World War Two. And let's look at this at this story. Let's say we're looking at World War II, and Britain was obviously Germany wanted to invade Britain, and there was the Battle of Britain, which was fought in the air, and the British were sending various types of bombers to bomb German cities. Like there was fierce bombing going on in Hamburg, in Dresden, that you may remember, and in Berlin, obviously. And the British had different types of bombers, like the Avro Lancaster or the Havilland Mosquito. And let's say that we look at one of them. Like this pretty much has the anatomy of a British Mosquito heavy bomber. And I was, let's say, like there was a squadron of bombers that was sent out to bomb certain German cities. And obviously, the Germans were using anti-aircraft guns. They had these flak towers that you may be aware of that were positioned in Berlin and Hamburg and so on that uh, were stuffed with anti-aircraft guns to try and get those bombers down. And let's say that if the bombers returned, the red spots indicate where the damage was done, right? So this is a bomber that made it safe back to UK, to England, and the red spots indicate where it was hit by enemy anti-aircraft guns. And then the question that was raised to the engineers is, where should we reinforce those planes? Where should we put extra armor on the planes to make sure that more bombers that we send out are going to make it safely back home? So where should we put extra armors if we know that the ones that return are being hit here, where the red spots are? So obviously, when you think very careful about it, you should not put extra armor on the red spots because those are the ones that made it safely back home. You should put extra armor or extra fortifications on all the unmarked places because you know that if a plane or a bomber was hit there, it's very likely that the bomber did not make it back home, right? So obviously you see that the engines here, they don't have any red spot, which is very obvious, right? As soon as you hit the engine, the plane is very likely to crash, and the cockpit as well. So the red dots are not the places that you should work on. You should work on the complementary or white space instead. And this very nicely illustrates the idea of bias. And that's a thing that we often witness in machine learning as well. I can tell you that every sample that you start off in machine learning is a bias sample because it's contingent or conditional on the state of a macroeconomy. It's conditional on the strategy the firm was adopting at the time frame the sample was taken, and it's conditional on the types of the customer behavior or endogenous effects of customers as well. So every sample is biased up to a certain extent, and that's not something to worry about. That's very important. That's something to be aware of, such that you can tap into it from an analytical perspective as good as possible. Um, what we often also have, well, not often, I have to say every now and then, is lack of predictive power. So we're given a data set and we have a few data scientists and they work on it and nothing comes out. That could be the case, right? I'm working with one firm now, for example, where it's really hard to to find predictive power in the data. The most funny example that I once worked on, I can tell you this now, it was for an international intelligence service. So you can think of FBI, CIA, MI6, MI5, one of those intelligence services I worked for. And they asked us to build a model that was gonna predict roadside bomb attacks in Afghanistan. And the data that we should use was data, all kinds of blog posts on Afghan blog sites. So they asked us to parse that and then build a predictive model. Obviously, upfront, we said there's no terrorist that is gonna let a bomb explode, and before that, just nicely announce it on social media. That's not the way how these people work. But yet, that intelligence service wanted to investigate that. So we came up with a model that had random performance, right? So we did all the parsing as it should have been done with natural language processing. We built some very complex models at the time, and we got an area under the ROC curve, for those of you who are familiar with that, of 50%, which means we had a random model. So that's an example of lack of predictive power. And if you face that, you can try and gather more data. You can do some clever feature engineering. It will not always solve the problem, but it might contribute and might allow you to gain a few percentage points of predictive power, or you can use Bayesian networks, for example. Bayesian networks or probabilistic white box models that are try to blend domain experience, business knowledge with knowledge or patterns that you learned from data. Development risk is another one. One you can see some. I can see I'm almost 1 hour. So, um, one topic that I will highlight is open source versus commercial software. I always tend to say there's nothing as expensive as open source software, and it's a very controversial statement because people will often say, obviously, open source software is free, but it's free, that's true. So there's a lot of R and Python scripts out there and packages out there. But first, it does not always come with the necessary quality guarantee that you should have. And often, um, you mean those packages are centered around technical aspects and not allowed around solutions, right? If you're building a fraud detection model, you want to have an end-to-end solution that starts from the data, that goes into the pre-processing, that goes into the model building, to the model evaluation, up to the fraud prevention. So it's a whole chain of activities, which is very difficult to automate using open source software, right? And which is more easy to automate using commercial software because commercial software vendors like SaaS, and we see a kind of resurfacing of MATLAB as well in the industry nowadays. Those are more centered around providing you with solutions rather than just routines or functions that are too much focusing on particular aspects or steps of the machine learning process model. Managerial risk is also one, model ethics, and there's also, I mean, this is now more relevant than ever before, climate change and ecological risk. Like in credit risk modeling, climate change and ecological risk is very important, especially if you're dealing with mortgage portfolios, because mortgages have a duration or a maturity of, can have a duration or maturity of 20 to 30 years. And it's very important to be aware of if you're financing a mortgage or if you're investing in a mortgage, where the collateral is situated. If it's situated in flood risky areas, yes or no. So that starts to become very important. Another ecological risk thing that you should be aware of is when you start training huge, overly complicated or highly complicated models. Like if you're doing blockchain mining, for example, or if you're using very complex deep learning techniques uh, that that need to estimate millions of parameters. Obviously, this requires quite a lot of computing resources, which can leave behind a huge ecological footprint, if you ask me, right? So there's a lot of work going on in that area as well. Okay, so this was more or less what I wanted to say. It's a lot of information, and I try to stick to 1 hour. In 1 hour, so we started with the machine learning process model, then we zoomed into the model requirements. We discussed statistical accuracy, we discussed interpretability, operational efficiency, profitability, and then regulatory compliance by means of privacy and ethics. We also said a few words about feature engineering and model risk. It is a very exciting area to work in. Both me and Seppa, we offer quite a lot of courses on these topics. In case you would be interested in one of our courses, we recently did a course on machine learning essentials for a big firm that had offices in Dubai and Saudi Arabia. Um, we did a 3-day course for them. We have a 2-day course on fraud analytics, a 2-day course on deep learning. We have various courses on credit risk modeling, on recommender systems, on customer lifetime value modeling, and more specific topics like Sepan is an expert when it comes to web scraping, for example. So he has a course on web scraping using Python. And I also have my online course website, which is bluecourses.com. Okay, so now I will have a quick look what questions came in through the chat and try to answer those. So there's a person that asks me what are SVMs. SVM stands for Support Vector Machine. It's a type of alternative to neural networks. It used to be popular 10 to 15 years ago, but now it's no longer popular. And actually, I don't think it's that relevant anymore as well. I think the power that is being offered by neural networks and especially deep learning neural networks can even, I mean, it's higher than what is being offered by SVM. So it's something that nowadays I would consider more of an academic thing than of something that is of practical use to you business practitioners. I have another question. Um, what about open source supported by big software companies such as the R release from Microsoft that supports their open source ML libraries? Well, it's the same thing with SaaS, right? SaaS has a product that is called SaaS Fire, which also allows to mix and match open source software with SaaS routines. And the thing is, I definitely think this is a good evolution, but what these firms do is they always use those open source software packages in the context of a framework of a solution for a particular problem. And that's what these commercial companies have to add, as I said earlier on. They're not that much focused on the technique itself, but they're focused on solving your business problem by providing you very pipelines, right? Analytical pipelines or machine learning pipelines that are end to end, that start at the data, that start with the data gathering, the data pre-processing, until the model being put into production, and all the types of other applications that come with it, right? So you can have in certain types of settings. Stress testing is, for example, a very important challenge, while these companies also will provide you with stress testing solutions, etc. Let's see where I have another question. Okay, I don't think I have other questions. No more questions. You can always, if you're interested, I'm more than happy to send you these slides for free. If you're interested in one of the courses that we're offering, do let us know. Yeah, I don't think I have any further questions. I do hope you learned something new, and feel free to stay in touch by email or whatever means. Okay. Thank you very much. Have a pleasant evening or a pleasant day. Bye bye.